surface over the complex numbers, irreducible, right? And what we've been looking at was the Hilbert scheme of points, right? We assumed that the irregularity of the surface is 0. And the kinds of things we've done so far is we've determined that the Hilbert scheme is smooth irreducible of dimension 2n. And we looked at the Picard group of the Hilbert scheme. And we saw that it was isomorphic to the Picard group of X plus the boundary divisor consisting of non-reduced schemes, but you know that, so this was B was, remember, the Hilbert scheme minus the configuration space, or you can think of the locus of non-reduced schemes. And we specifically concentrated on P2n, right? So let me remind you what that was. So we had two types of divisors in that case. The Picard rank was 2. So one was you fixed a line, and then this was H, and it was the locus of the class of the locus of schemes such that this Z such that the support of Z intersect L is non-empty. Informally, the way you can think about it is that the schemes with n-1 points at random places, but 1 point on the line, okay? And this was also the pullback of the ample generator of the map. So remember, we had the Hilbert-Chow morphism from P to N to P to N. So this was Hilbert-Chow. And if I take the generator here and pull it back by this Hilbert-Chow morphism, then I got, you know, the class of that was H, okay? So those were our two divisors on P2n. We had the boundary divisor and this H, and we discussed what the ample cone was last time. So the ample cone of P2n, we decided was the cone spanned by n-1 H minus B over 2 together with, sorry, H. And let me again, usually we were denoting this like this. We were putting H there, B there. So this is somewhere here. And you see there were geometric interpretations for both of these rays. What were the geometric interpretations? As I said, H is the pullback of the generator by the Hilbert-Chow morphism. And to get this one, what you did was you look at polynomials with degree n-1 vanishing on your Z. This is a subspace always of H0 of OP2 of n minus 1. So the way you should think about it here is you have polynomials of degree n-1 on P2, homogeneous polynomials of degree n-1. And those that vanish on Z is always a codimension and subspace of that. And so that gives you a map from this Hilbert scheme to the Grassmannian. Let me call the dimension of this thing, I don't know, capital N maybe. So capital N minus N to capital N. This, of course, is nothing other than N plus 1, choose 2. Okay. And so what we saw last time was that this was a morphism, but it did contract the locus of points that lie on a fixed line. So that you see that we knew what the ample cone was, and we had fairly explicit geometric characterization. And you see, in fact, you can do this kind of thing so for many other surfaces, like, you know, if you want to do P1 cross P1, or, you know, Hirzebruch surfaces or Del-Pezzo surfaces, at least if the degree of this thing is bigger than 1. The degree 1 case is a little bit more complicated. You need a little bit Brisbane stability to be able to answer that one. Okay. And now what we were discussing were the effect was, we were now discussing the effective cone of the Hilbert scheme of points, right? And let me also briefly remind you what we did. We first looked at the cases n equals 3, 6, 10, 15, and so on and so forth. And what we saw was the extremal effective divisor. So again, let me remind you so here we have n minus 1 h minus b over 2, and here we have sort of the edge of the effective cone. B was always in the edge of the one edge of the effective cone. The interesting edge of the effective cone is finding this one. So as I said, the Hilbert-Schemes morphism, right, gives us one edge of the ample cone and one edge of the effective cone. The interesting one is finding the other one. And what we saw in these cases was when n was, I don't know, what's it? K times, okay, so let's see, k plus 1 times k plus 2 over 2. All right, so when k is 1 is 3, when k is 2 is 6, and so on and so forth. Then what we saw is that the extremal effective rate was given by z that failed to impose independent conditions, that fail to impose independent conditions on OP2 of k. In other words, if you have 3 points, then you have 3 points that fail to impose independent conditions on O of 1. Of course, the pedestrian way of explaining that is that when the 3 points are collinear, right? Similarly, if you have 6 points, then that we are looking at 6 points that fail to impose independent conditions on O of 2. Again, the pedestrian way that you would think about this is that, you know, it's the set of 6 points that lie on a conic, and when it's 10, it's like set of 10 points that lie on a cubic, and so on and so forth, right? The first interesting case that we were discussing was n equals 12. And then I tried to convince you that there, what we should look at is the tangent bundle of P2 twisted by 2, okay? And then what we want to do is we want to look at schemes of length 12 such that, you know, H0 of TP2 tensor twisted by 2 tensor IZ is not equal to 0, okay? Now I claim that this is a divisor and it's an extremal divisor. So this is a divisor, an extremal divisor, in fact. Now you see, stuff becomes a little bit harder when you had a line bundle, when you ask about points that fail to impose independent conditions on the line bundle, it's easy to see that like that's a divisorial condition, because you see what happens is that, you know, general points always impose independent conditions on sections of line bundles. Now, it's not so clear that if you have a higher rank bundle, right? I mean, again, the reason why that's easy to prove is that what you do is you choose your points successively, and all you have to do is that each time you need to find a point that is not contained in the 0 locus of a section of the previous points. So each time you need to drop the dimension by 1, and, you know, saying that the dimension of a subspace is 1 less just means that the two are not equal. Now, if you have a rank 2 bundle, or more generally, let's just say it like this. So suppose that you have X and you have a rank R bundle, right? Now, you see, if you ask that the section of this E, vanish at the point P in X, right? You would expect that to be R linear conditions, R linear conditions. In other words, what that is that over that point P, right, you have the fiber of this vector bundle, EP, right? And what you want is that you have the 0 vector in there, right? I mean, to say that like the section passes to the 0 point instead of just a random point of this R-dimensional vector space should be R linear conditions, yeah? So that, in other words, if I choose n points, right, P1 through Pn, and ask that sections of E vanish at these points, right? You would expect there to be that to be R times n conditions, right? And, you know, this is if you were, you know, a beginning linear algebra student and you thought that, you know, if you had Rn equations, then, that cuts down the dimension by Rn, that's what you would think. Of course, we all know that, sometimes these conditions are not independent, right? So what you need to show is that these really, like, first general set of points do impose independent conditions in sections of the tangent bundle twisted by 2, right? And, so that's what you need to do. And it's not so easy anymore. And, in general, it's not true, right? I mean, if I have a random bundle here, then it's not true that, sections that vanish at a collection of points, there's really that many conditions. Let me give you an example, right? So, like, for instance, your bundle of rank 2 can be O of 1 plus O of 2, right? So here is a perfectly nice bundle, right? So what are the sections of this thing? So the sections of this thing, H naught of E splits, right? So you have H naught of O1 plus H naught of O2. So these are linear forms and quadratic forms. So there are 3 linear forms and 6 quadratic forms in P2. So altogether, it's a 9-dimensional vector space, right? But now what happens here is that as I add points, right? If I take 3 points in P2 and ask that the sections of E vanish at those 3 points, right? What happens is that there are no more sections of the linear forms, right? You kill all the sections of the linear form, and there are 3-dimensional space of conics that pass to this point. So once you put these 3 points, then, you've killed all these sections, and you've reduced these sections to 3. Now, if you add 1 more point, right, you can only start decreasing the sections by 1. Right? So that you see that it's not growing like up to 3 points. It really grows like you impose 6 conditions, with the 4th point now imposes only 1 condition on the sections, right? Because once you put these 3 sections, you've already killed all these sections, right? So what's left, the 3 sections that you are left come all from this, right? And each time you impose 1 condition, but not 2 conditions anymore, right? So you see that and this gets at the heart of like what's different between a bundle like this and a bundle like the tangent bundle of P2. And that's what I want to talk about today, and that's the stability of this bundle, okay? That's where we are headed, okay? So let me give you a proof nonetheless that the general set of points, right? General set of 12 points do indeed impose independent conditions in TP2 of P2. So general set of points, general set of 12 points impose independent conditions on TP2 of 2. Now you see for this what you need to know. I mean, if you want to compute cohomology, oh, there is a chat, let me see. Okay, no, all right. So, if you want to compute the cohomology, what you need to do is you need to find a resolution of a general set of 12 points. Now, suppose you have like a general set of 12 points, then you see you can look at cortex that contain those 12 points. So there's a 15-dimensional vector space of cortex, right? If you ask that they vanish from these 12 general points, you get 3 cortex, right? So you get a map from O of -4, 3 copies, given by the 3 cortex that vanish at those points, right? And it's the fact that those generate the ideal, and then the co-kernel of that thing, there are 2 degree 2 relations, syzygies among those. So the resolution of a general set of 12 points looks something like this, okay? And now we want to compute, so we twist this thing by the tangent bundle of P2. So what I get is I get TP2 of -4, 2 copies mapping to TP2 of -2, 3 copies mapping to TP2 tensor IZ, okay? TP2 of 2 tensor IZ. Now the key point here is that like HI of TP2 of -2 is 0 for all I, and HI of TP2 of -4 is also 0 for all I. You can check these things easily using the Euler sequence, yeah? And then what you see is that then you see because all the cohomology here vanishes, then the cohomology here has to vanish as well. So what we learned is that for a general set of 12 points, we really have that H0 of TP2 tensor IZ is equal to 0. Okay, so in other words, this condition that we had, this Z in P12 such that H0 of TP2 of 2 tensor IZ is not equal to 0 is not the whole moduli space, right? So there are Z which don't satisfy this condition, okay? And then it's relatively easy to show that this is a divisor and to compute the class. In fact, you know, maybe I won't go through this, but you can compute the class of this thing. So the class of these things will always be something like this. So I guess it's 3/2 TP2. So I add 2 to it. So it's 5/2 H minus B over 2. And then, you know, if you really want the class, then you multiply by the rank, which is 2. Okay. But this is, no, 3/2. What do I do? 3/2 plus 2 is 7/2. So 7/2 H minus B over 2. Okay. Anyway, so you can compute the classes of these things, and the thing here is the slope. Okay, slope of TP2. Okay. All right, so now let me explain various things about these things. So what's so special about this example? First, like, what are some aspects? First of all, I had to guess that I had to find this bundle. Somehow I pulled this out of a hat. I didn't really explain to you, how do we know that we needed to look at this bundle? How do we know which bundle to look at? So that's one question, right? The other thing that I have to explain to you, you know, I knew that I needed to look at this resolution. So I somehow knew the resolution to look at. How do we know which resolution, how to resolve IZ, right? And then the final thing is that, you know, like, we needed to use that resolution to know that this thing was a divisor and not the whole thing, right? We needed to check that we really, the general Z does not satisfy. The general Z, you know, has this H not equal to 0. Okay, so let's start introducing these things and explain how you do it in general. Okay, so the first thing is, all right, so maybe let me start by introducing stability. Okay. So the way to think about this is when we looked at this bundle O of 1 plus O of 2, right? Compared to maybe TP2, let me make it TP2 of -1 if you want, right? No, maybe just TP2, sorry. Just TP2, okay? So now you see this is rank 2, and the first Chern class is equal to 3. This is also rank 2, and the first Chern class is equal to 3, right? But you see, there is a big difference between these bundles because this has a sub bundle like this, O of 2, mapping to O of 1 plus O of 2, going to O of 1, right? So what it has is that this is a this has a slope. So, okay, the slope of this thing is 3/2. The slope of this thing is 2. So what does it mean to be the slope? So let me introduce the slope first. And this you can do on any surface or really on any variety. Suppose that you have a surface together with an ample. So this is an ample. This is a surface. All right. Then you see what I can do is I can talk about, and I say that I have a torsion-free sheaf. Okay, so then the slope, and the slope depends on the ample that you've chosen. So the H slope of V, right, is the first Chern class of V dot H divided by the rank of V, okay? All right, so now you see the first Chern class here was 3, the rank is 2, so you see that the slope is 3/2, and the first Chern class is 2, and the rank is 1, so you see that the slope is 2, right? And now what's very special about this bundle as opposed to this bundle is that it has the sub-bundle with a bigger slope, right? 2 is bigger than 3/2, okay? So let's make that into a definition. So definition, a torsion-free sheaf on X, let me give it a name, torsion-free sheaf V, maybe, whoop, what was that? Torsion sheaf V on X is called slope semi-stable, mu H semi-stable. If for all W proper subsheaves, right, what you have is that the slope of W is less than or equal to the slope of V. All right, so in other words, you see here is an example, right? This O of 1 plus O of 2 is not semi-stable, right? Because it has this O of 2 sub-bundle with bigger slope. On the other hand, the tangent bundle of P2 is semi-stable, okay? So examples here. O1 plus O2, not mu of O of 1, semi-stable on P2. On the other hand, TP2 is. So now why is that? Let's remember, let's prove that. So you see, to say that, so remember what TP2 looks like. We have the Euler sequence, right? Right? And now what does it mean for TP2 to be semi-stable? So, you know, if I want to have like a proper sub-bundle here, right? So like, you know, if it's not the whole thing, it will be a rank 1 sheaf, right? So if you have a line sub-bundle of this, so the slope of this thing is 3/2. A line bundle has integer slope if it's going to be bigger than this, right? So then you have to be O of K has to map to this, right? With K bigger than or equal to 2. But you see that doesn't happen, right? So, so the question is OK TP2 non-zero for K bigger than or equal to 2? And the answer is no, right? So, so this is equivalent to looking at H naught of TP2 of minus K, right? If I look at that, twist the sequence by minus K, so you see that you have O of minus K mapping to O of minus K minus 1, mapping to TP2 of minus K, right? And we are asking whether this has any sections. But you see, if K is, sorry, this is a +1. I don't know why it's not okay. So you see, if this K is greater than or equal to 2, this is negative, so they don't have any sections or any H1. So you see that H naught of this thing is 0 if K is at least 2. So you see that this TP2 of 2 is stable, right? And this will be the main sort of difference between, like, you know, in choosing which bundles that we want. So if we want to make, you know, sensible divisors, then we need to stick to stable bundles, okay? All right, so let me just make one more definition. So this definition, this slope definition is useful, but we want what's called Giseka semi-stable. So let me define that as well, okay? So what you can do is that given a torsion, given any sheaf actually, given any sheaf E, pure dimensional always, coherent sheaf. So I'm not going to say coherent and pure dimensional. What you can do is you can associate to that the Hilbert polynomial. So I think maybe I want to do it like this. the Hilbert polynomial. And what is that? This is the Euler characteristic of E times MH. Okay, it's a polynomial. So since we are on a surface, let me assume that this is torsion free. I mean, you can do this thing for torsion sheaves as well, but let me just, for simplicity, assume that this thing is torsion free. Then it starts as A2 times m squared over 2, right? Plus lower order terms, and this is the rank of, this A2 is really the rank of, yeah. All right, so that's the Hilbert polynomial, right? The usual Hilbert polynomial. It depends on your ample, it depends on your sheaf. What we do is we define the reduced Hilbert polynomial. And this will be denoted by small p, which of course is hard to tell from a big P, but you know, this was a big P, this is a small p. It's just this divided by this leading coefficient, okay? So that you normalize, just like when we defined the slope, we normalized it by the rank, right? Here again, you normalize by the rank, okay? All right, so now what you do is that you can define the notion of Giseka semi-stability, and the definition is really analogous to the definition of the slope semi-stability. So instead of using slopes to measure things, you just use the reduced Hilbert polynomial. So you say that E is Giseka semi-stable if for all proper subsheaves you have that the reduced Hilbert polynomial for F is less than or equal to, and again, you know, if you don't allow equality, you get stability. If you allow equality, then you get semi-stability for that of. And what does it mean for a polynomial to be less than or equal to another polynomial? This inequality should hold for all sufficiently large m, okay? All right, let me take a little break and see whether there are any questions. Any questions about the definition of slope semi-stability, Giseka semi-stability, and so on and so forth? The thing that you should know is that slope stability implies Giseka stability, implies Giseka semi-stability, implies slope semi-stability. So these notions are pretty close to each other. They are not always the same. There are like subtle differences between them, and we can do some examples, okay? All right, so in general, if X is a random surface, like in general, it is hard to classify stable bundles on a surface. All right. I mean, you know, when do they exist? For which Chern characters do you have them and things like this? This is a hard problem. There are exceptions to this thing. It's relatively easy when X is a K3 or an abelian surface. So these are usually the easiest cases where the classification is sort of the simplest. And, you know, it's done, and I'll explain it to you when X is P2. And then in general, we know very little. Like, you know, there are general theorems that tell you when they exist, but like, you know, and there are some restrictions that tell you for certain invariants they can't exist. But, you know, there's usually a gap between these. Okay, so what I'm going to do next is I'll explain to you the classification of stable vector bundles on P2. Okay, this is the Drezel-Potier classification. All right, let me introduce one more invariant. So like, so here is what I should have said. Okay, there is an important thing that I should have said before going on with this. The key point here is that Giseka and Maruyama, building on work of Mumford, these are separately, but you know, secretly, of course, one should put Mumford here as well. What they've done is that they've constructed moduli spaces parameterizing stable bundles on varieties. Okay, so let me just state the theorem for surfaces, because you know we've been talking about surfaces, but you know this you can do more generally in higher dimensional varieties as well. I mean, Mumford was the first one to really do it for curves and study it in detail, and then you know they extended this to Giseka and Maruyama, again following most of the ideas of Mumford, have extended these things to higher dimensions. So here is what you can do. So let me introduce. So you know the way you should think about stable bundles is that they are building blocks of all bundles. So what does that mean? Supposedly you give yourself a vector bundle, then this has a filtration, or you know a locally free, let's say a torsion-free sheaf. Torsion-free sheaf, then this has a filtration like this. So, you know, you have E naught, maybe this is equal to 0, contained in E1, contained in E2, and at some point, let's call it EJ, it becomes equal to E, okay? So you have a filtration with the property that if you look at the successive quotients, so Fi will be EI, mod EI minus 1, okay? So these things are semi-stable sheaves. Okay, so what is this saying? What this is saying is that every sheaf has a filtration by these semi-stable sheaves, right? And furthermore, it has the property that you know, the invariance decrease. So if you look at the reduced Hilbert polynomial of F1, then that's bigger than the reduced Hilbert polynomial of F2, the last one, I guess, is Fj. Okay? This is called the harder Narasimhan filtration. And the way you construct this is basically the way you would think to construct it. So what you do is you take your E and you find like a maximal, you know, you find a subsheaf with the maximal reduced Hilbert polynomial. You make that your E1, then you take the quotient and then you do it for that, and you take the quotient and so on and so forth. There are some things that you need to check that this thing stops. I mean, but it stops because in this case, the ranks, I mean, you know, the rank is this, you know, finite positive integers. So, you know, you can't keep doing this, right? And then you need to say that it's well defined and all those things. But, you know, modulo that kind of thing, right? It's easy to imagine how you would prove this. And this is called the harder Narasimhan filtration. And then the way you should think about this is that the stable bundles are the building blocks for all bundles, okay? And then the next point to make is that even if you have a semi-stable bundle, so if E is semi-stable, then what you have is a Jordan-Holder filtration. What that means is that you can factor this E into, you know, again, let me say it like this, right? With the property that now these factors are actually stable, not just semi-stable, but stable. This filtration is not unique. So this one is unique. This is not unique. Okay. I mean, you know, for instance, if you had just the direct sum of two things, you could reverse the order or whatever. So, but what is unique is the factors themselves are unique, or the associated graded is unique. The associated graded object is unique. And what it is that you call two semi-stable bundles S equivalent. E and E prime are S equivalent if they have the same associated gradient. These are semi-stable. They have the same associated gradient. Okay? So if the factors of the Jordan-Hölder filtration for E and E prime, two semi-stable bundles, are the same, then you call them S equivalent. And then here is the theorem of Giseka and Maruyama. So here you have your smooth projective surface, you have your ample, right, as usual, and you fix a Chern character. So this is a Chern character. So you specify the rank, the first Chern class, and the second Chern class of your bundle. Then the theorem is that there exist projective moduli spaces. So I'll typically denote it like this. So this is these are projective moduli spaces parameterizing S equivalence classes of Giseka semi-stable sheaves. Okay, so there are these moduli spaces. That's the key point. And then again, we've already seen one example of this. So if I look at P2, if I look at the surface where the irregularity is 0, right? Then when the rank is 1, this MXH, 1, let me call it 0, N maybe, is nothing other than the Hilbert scheme of points. I mean, again, it depends on what I'm using. So let's just say this is the rank, this is C1 equals 0, and this is C2. C2, I should say. Let's see, C2 should be minus and the Q2 should be on. Let me just. I think this should be Q2, should be and. So then that's just Xn, okay? So the basic example is the Hilbert scheme of points when the rank is 1. But of course, as the rank increases, these moduli spaces get fairly complicated, right? And, there are many questions about them. So many questions, when are they non-empty? When are they irreducible? What's their dimension? What's their topology? All of these questions, So there are various answers to these things, either when X is special or like when V is special. And I'm not going to describe these things here. This would be like a subject for a different kind of lecture. But what I want to do is go back. So let me remind you how we got to this thing. And this is what we want to do is we want to talk about the Dresser-Potier classification of stable bundles. Okay? All right, so what I want to do is I want to tell you when are these non-empty for P2. Okay, so that isn't that minus n instead of n. Okay, I'll make a minus n. The plus or minus, how about we do it like this so that we don't have to think about it, okay? I mean, you can figure this thing out by just writing down the sequence, and now I don't want to do it. Okay. All right. So now, when are these non-empty? So I want to look at MP2 of V, and the question is, when is this non-empty? Okay. All right. So now let's start talking about this. This is due to Dresser and Potier in the mid-80s. I need one more definition, and that's the discriminant. So the discriminant is a half times the slope square minus Q2 over R. It's another way of describing the second Chern class. So, there are many ways you can denote this thing. You can do RC1, C2, or you could do R21, Q2, And then finally, what you can do is you can also do R slope discriminant. Okay, and these are equivalent ways of describing the churn class or the churn character of the bundle. So, if I know the slope and the discriminant, then I can read Chi1 and Chi2. And if you know Chi1, Chi2, you can work out C1 and C2, okay? At least if you can keep your signs right. And this is something that I always mess up, so I'm not going to try to do it here. Okay? And this is the discriminant. The importance of the discriminant is like this. There is something called the Bogomolov inequality. Bogomolov inequality, and this is really important. And what it says is that if you have a slope semi-stable bundle, so if this is slope semi-stable, then it says that the discriminant of this bundle has to be greater than or equal to 0. And you see that this is really an obstruction for the existence of semi-stable bundles, right? The problem is that if this is not satisfied, then you cannot have a semi-stable bundle with those invariants, okay? All right. Okay, so now let's come to the Dresde-Lopotier classification. Okay. So first of all, there are some bundles that we do know, right? Like line bundles are perfectly nice. Line bundles are perfectly nice, stable bundles, right? It's easy to see that these line bundles are rigid. They don't move. They are the unique points of their moduli space. So the first thing that we can try to do is, can we understand rigid bundles, okay? So here is the definition. A semi-stable bundle is exceptional if the following thing happens. If you have that xi EE, so this is my bundle, EE is like this. First, this is equal to C if I equals 0 and 0 otherwise. Okay? What's that? There is a question. I think it's R22. No, it's this. The discriminant is correct. It's a half mu square minus G2 over R. The thing is that sometimes people define their discriminant as R delta or something. I really want to use this. This is the definition I do want to use, okay? So XIEE, what just happened? Sorry. Let's try that again. Okay. All right. So now let's understand what the exceptional bundles are, okay? So the way you understand, so first of all, the line bundles are exceptional. So these are exceptional. And it turns out that you can make new exceptional bundles from old ones by something called mutation. Mutation. So now what's a mutation? The mutation is like this. So like you see, I have a map from O to O of 1, tensor hom O of 1. So let's start like this. O of 1, O of 2 is a strong exceptional collection, okay, for P2. What that means is that, the only X are hums from left to right, and there are no other X anywhere. And then, the derived category is generated by these three objects, okay? So now what I do is I take two of these guys, right? So you do O of 1, hom O to O of 1, right? That's like this. And then I have a co-kernel here. Of course, this is a very fancy way of writing the usual Euler sequence, right? O goes to O of 1, 3 copies, and then here you get the tangent bundle. So this is called the mutation, and then, you know, there is a right mutation and the left mutation, and if I could ever remember which of my hands were right or left, you know, life would have been much easier for me, but, you know, I can't. So it's one of the mutations. So like the way you should think about this is that you take this exceptional sequence and you could do this construction with either these two or these two, okay? And I suppose that maybe you call this one the left one and this one the right one or something, okay? But anyway, it's a mutation, and the key point here is that this now the tangent bundle of P2 is also exceptional. Okay. And, you know, you can keep going. So now, like, you know, if you wanted to make another one, right, you know, you can now take O of 1 and TP2 and keep doing it. So you could take O of 1 and take TP2, you know, now 3 copies. Again, the way you think about this is this tensor hom O of 1 to TP2, right? And then, you know, so again, the way to think about this is just the 3-dimensional vector space, right? So what you get is, you know, you get a map from O of 1, so you have TP2 of 3 copies. Now you get a rank 5 bundle here. So this is a rank 5 bundle. So let me put it here, which is, so to speak, the next exceptional, and so on and so forth. So what you can do is you can start with the standard exceptional collection and just do infinitely many mutations to your heart's content, and you generate a whole collection of bundles, and these are exceptional bundles. Okay, again, you know, these are not that hard to check. You need to chase some diagrams to see that these kinds of conditions are satisfied, but let me not do that. But the key point here is that you have these exceptional bundles, and you know how to get them. You start by line bundles, and do a sequence of mutations. So this generates for you infinitely many bundles like this. And, you know, their ranks grow, right? I mean, we started with line bundles, now we have rank 2, this is rank 5. You can keep doing it and get, you know, larger and larger rank bundles like this. And they have the property that the moduli space is a unique point. The moduli space is a unique point. Okay. And in fact, we can say a little bit more. So for instance, we can determine the discriminant. You know, the discriminant, right? The key point here is that the discriminant of an exceptional bundle is always less than a half. The way you can do this is that you can use Riemann-Roch. So Riemann-Roch I suppose what I should have done is I should have told you what Riemann-Roch here is, but you know, if we look at chi-e-e, right, then this is the rank of e squared times p of 0 minus 2 delta. Okay, p here is of course, you know, the is just, you know, whatever it is, x plus 2 choose 2, right? P of x is x plus 2 choose 2. X plus 2 choose 2. Okay, it's the Hilbert polynomial of O, right? Okay, so now if you do this, you see that we know that this guy is 1, right? Because chi-e-e is the alternating sum of the dimensions of the x, right? And, you know, hom EE is one-dimensional and all the higher x di's are 0, right? So from there, you can work out what the discriminant is. This is 1, right? So I get that the discriminant has to be a half times 1 minus 1 over r squared or something. Let's see. 1 minus 1 over r squared. Okay, so in fact, the discriminant of an exceptional bundle is just determined by the rank. Okay. Okay, and you see that it's always less than a half. Oop, what did I just do? I don't know what I just did. Can we hide this thing? Okay. And it's always less than a half, okay? So now what Dresser and Lepotier say is that what you should do is you should plot. So here will be the slope, here will be the discriminant, right? And so far we know that we have O, which occurs here, and O of 1 occurs there, right? So this is 0, here is maybe a half. Here, when you look at a half, you have like the tangent bundle TP2 twisted by -1, right? It happens at 3/8, so this wasn't maybe such a good, I should draw it a little bit higher. The discriminant there is 3/8. We found this rank 5 bundle, which, you know, happens somewhere there, and so on and so forth. Okay, so, and by doing these mutations, you can find like infinitely many of these exceptional bundles. Okay, now the observation of Dresser and Lepotier is that each exceptional bundle forbids the existence of semi-stable bundles. So let's see what happens. Suppose that I do have an exceptional bundle E. Let's call it E alpha, exceptional bundle of slope alpha. Right, the slope determines both the rank and the discriminant. I told you how the rank determines the discriminant. The slope, you know, the rank of a exceptional bundle with the given slope is the minimal integer that makes the slope an integer. So that if r times alpha has to be an integer and r has to be the minimal number such that that's an integer. The reason is, again, because the Euler characteristic is 1, you can write this thing in terms of the slope, and then you see that, like, you know, the rank and the slope are relatively prime. Okay, the rank and the first Chern class are relatively prime. I mean, I wrote, if you write down Riemann Roch in terms of C1 and the rank, then you see that they are relatively prime because the Euler characteristic is 1. Okay. All right, so now we have our exceptional bundle. So now suppose that I have a stable bundle, right, whose slope is close to alpha. Let's say that the slope of f is less than alpha, but close to alpha, not too apart, not too far apart. Let's say that alpha minus mu of f is less than 3, okay? All right, so now let's see what that means, okay? The first observation here is, oh, Justin is asking a good question. Do all the exceptional bundles arise in this way? And the answer is yes. So I was going to say that in a second, and, you know, by our description, so the proof of that thing will fall out in some sense, okay? The question is, do all exceptional bundles arise the way I described it, namely starting with these line bundles and doing mutations? And the answer is yes. Though that's not so obvious, but it will become more obvious in a second, okay? All right, so the observation is like this. If the slope of two stable bundles are close to each other, then there is no x2 between them. So here is an observation. This is on P2. So say that you have F and E stable bundles or semi-stable bundles, right? And then their slope is close. So then, like you see, let's look at x2 fe. So then you see that this is, by Serre duality, the same as Hom E f minus 3 dual, right? But you know, if the slope of f was close to the slope of e, in particular, if they were within 3 of each other, right? Then I subtract minus 3. So what did I want here? So the condition here is, so like if mu of e is bigger than mu of f minus 3, right? Then this is 0. You can't have, if you're stable, right, or semi-stable, you can't have a map from a semi-stable bundle of higher slope to a semi-stable bundle of lower slope, right? Because then the image, right, which would have greater than or equal to slope greater than or equal to of E, would be a sub of this, which would, you know, violate the semi-stability. So that you see that if you have this kind of thing, then you don't have to worry about x2 too much. The x2 vanishes, okay? All right, so then what does this mean? So I'm assuming, so in particular, you see what this means, that if I look at the Euler characteristic from E alpha to F, right? So what does this look like? So remember, this is just Hom E alpha to F minus x1 E alpha to F plus x2 E alpha to F, right? What we just said, this the x2 is 0, right? But now you see the slope of f is less than the slope of E alpha, right? So then there is no Hom either. So the only thing that you can have is x1. In other words, this Euler characteristic has to be non-positive. It has to be less than or equal to 0, okay? What that means is that I can express this. So this x2 fe, x2, this chi E alpha f, I know how to write it down, right? It's the rank of E alpha times the rank of f, right? Times p of the slope of f minus the slope of E alpha minus the discriminant of f minus the discriminant of E alpha. Right? That's just Riemann-Roch. Right? So this is Riemann-Roch, what this is telling you, and we are saying that this is less than or equal to 0. In other words, you see what this means is that the p of the slope of f minus the slope of E alpha has to be less than or equal to delta f. Maybe I just put the delta E alpha over here. Okay, so you see that you get a quadratic inequality. So, you know, if you, this is the slope in our, let's go here, this is our y-axis, right? This is our y-axis, and then here is our x here, right? So you see that I get some sort of quadratic inequality. There is a similar thing that you can do if instead of, if I had assumed that instead of saying that the slope of f was bigger than alpha, I could have assumed that the slope of f is bigger than alpha, right? So this was, I'd assumed that it was less than alpha, right? Then you would have a similar thing, that a similar arguments would say that chi f E alpha has to be less than or equal to 0, and you get another such quadratic inequality. Okay, and then what you can do is you can plot these things in your graph. So, you know, the fact that there is O here, it means that there is some region, which I didn't draw so well. So let's delete this things. Okay, so there is some region here, right, where, you know, the only stable bundles because of this existence of O can lie over here. Okay, it's an inequality on the discriminant. This discriminant has to be bigger than some value, and you know, these are some explicit quadratic polynomials given by, you know, if I put O there, of course, then what this is saying is that you know, mu of f plus 2 choose 2 has to be less than or equal to delta of f, right? So you see this is an explicit quadratic polynomial for the discriminant in terms of this is the y-axis, this is the x-axis, right? And if you were to plot this, you would get, you know, this thing. Similarly, the tangent bundle tells you something. O of 1 tells you something. The next bundle here tells you something. The next bundle there tells you something. And, you know, this curve is a pretty crazy curve. It's like a fractal curve. Like, you know, as I said, there are infinitely many exceptional bundles here. There's one here, one there, you know, one there. And, you know, these peaks get smaller and smaller, but there are infinitely many peaks. And that's like really a fractal curve, like fractal-like curve, okay? But what sort of the simple consideration told us is that if I want to have any stable bundles, then they have to lie above this curve, okay? And, you know, there is some max-min process that you have to do. You know, I'm just saying that, like, you know, you look at the closest guy here, right? I mean, how do you know that an exceptional bundle here doesn't give you other restrictions? It doesn't, because, you know, these peaks, like, you know, sort of, if you look at the line, the discriminant equals to a half, like, you know, O in this region dominates it until these peaks hit a half. And then, like, you know, the other peak, like, dominates it when it's those peaks hit a half, and they are all disjoint, okay? So now to answer Justin's question, like, how do we know that there are no other exceptional bundles other than the ones that we already got by mutating? The answer is that now if you look at all these peaks and look at the complement of those peaks, right, then there are simply no rational points left. So you know that there can't be other exceptional bundles, okay? I mean, you know, there's obviously some combinatorics and some work to be done to prove the claim that I'm making that there are no other rational points left, but the proof is by showing that you exhaust all rational slopes, okay? All right, so far what I did is I told you like, what are the restrictions on the existence of stable bundles, but then there is a converse to it as well. So let me tell you the theorem. This is due to Dreze and Potier. And they say the following thing. So MP2 of V is not non-empty if and only if either V is exceptional, V is semi-exceptional. Semi-exceptional means that it's a multiple of an exceptional character, or V lies on or above the Dreze-Potier curve. Okay? So in other words, that is the picture. So, you know, you have this curve that we just described, this fractal curve. This is like a half. So, you know, if you want a moduli space, a non-empty moduli space, you either have to pick one of these exceptional points where your moduli space is a single point, or you have to be on or above this curve, this fractal curve. Okay? So that's the classification of stable bundles. Now, what's the relation? Why am I talking about this? Remember, we wanted to make effective divisors. Let's go back to our description of the effective divisors on the Hilbert scheme, right? This was way back how we started it, or what we discussed last time, right? What we wanted to do is, the way we wanted to make effective divisors was ask that points fail to impose independent conditions on sections of a vector bundle, right? And I hope I was able to convince you that if you want to get sort of a sensible divisor, then you can't have some subsheaves that have too many of these sections. So this bundle had better be stable, okay? So then by getting the classification of stable bundles, then we have a way of thinking about which divisors we can look at, okay? So these divisors go under the name of Brill-Noether divisors. So let me tell you what they are. And in fact, what you can do is you can define these things for the moduli spaces more generally. So let me do that. So say that you have two moduli spaces. Okay, so you have two moduli spaces, but the thing that I want to happen is I want the Euler characteristic of these, the tensor product of these Chern characters to be 0. Okay, so then here is what you can do. I mean, you can choose your favorite bundle here. Okay, and now I'll define for you a divisor, and let me put this thing in quotes, right? So I'll define for you a Brill-Noether divisor on this moduli space. So what you do is you define this DE. So this will be the set of all F's. So this will be the set of all F's in your moduli space with V1, right? Such that, you know, the cohomology of F tensor this E is not equal to 0. Okay, and we've seen this already, these kinds of things, right? So for instance, when I was talking about the Hilbert scheme of 3 points, right? Then what I did is I took O of 1, and then, you know, I looked at sets of 3 points such that H0 of IZ of 1 is not equal to 0, right? And this was, you know, a complicated way of saying that locus of 3 collinear points. Okay. But you know, you can define these Brill-Noether divisors, right, in general for any moduli space, right? So what you could do is you take your E and you want those sheaves such that they have some unexpected cohomology. The tensor product has an unexpected cohomology. Now, what's the problem? The problem is that you don't know that these are divisors necessarily. That's why divisor is in quotes, right? The danger, I mean, there's a danger here. Danger is that, you know, it could be that Hi of Fe tensor E is not equal to 0 for all F in the moduli space, right? And this can really happen, right? I already gave you an example of that as well, right? So if I take O of 1 plus O of 2 to be my E, for instance, right? And then I don't know how many points you want to put, but say that you want to have 4 points, right? If I had 4 points, right? I mean, I guess the Euler character, you can't quite make the Euler characteristic 0 here. So let's see. So let's maybe do O of 2 and O of 3, right? So then this guy has 6 sections, this has 10 sections, so this is 16 sections together. So let me do Z 8 points, right? Say that this is 8 points, right? So now you see, if I look at IZ of 2 plus IZ of 3 and compute the cohomology of this thing, right? I mean, even if you had, you know, even if you had 8 general points, right, then you see that this doesn't have typically any sections, but this has 2 sections. So that you see that the dimension of this thing is greater than or equal to 2 for all Z, right? And then, you know, even though you expected it to be 0, the Euler characteristic was 0, you see that, you know, it's not a divisor, it's the whole space has this property. right? So the issue that comes up is that you need to know when is this a divisor? When is, what happened here? When is something like this really a divisor? And to do that, what you need to do is you need to say that the general member of the moduli space has this cohomology equal to 0, okay? So let me tell you the theorem and maybe briefly sketch in the case of P2. This is, by the way, a very active area for random surfaces. It's like very closely related to questions like S duality, strange duality, and things like this. So I'm just going to give you a small taste of the answer in the case of P2. And, you know, I mean, you know, the way I'm taking these lectures is that I'm just telling you enough to get you interested in the problems and sort of point out what some of the difficulties are rather than giving a general survey of what's known, which I couldn't have done in 4 lectures anyway. But all right, so let me tell you what the answer is in case of P2. So here is the theorem. And I've been a little bit lax in saying, attributing my theorems. So like, you know, this joint work with Jack Huizinga and Matthew Wolf, but here is what it says. And it says that it's, so maybe before I say the theorem, let me draw a picture first, okay? So here is our Drezil-de-Poitier curve. It's this crazy fractal curve, okay? So now you see, in order to define this Brill-Noether divisor, for this to be an expected divisor, right? So we had to have that this Euler characteristic be equal to 0, right? So now choose your favorite moduli space. Let me actually change my color. Say that I have, maybe let's make it more pink. So say that I have my moduli space. So this is on P2, age is determined, so you have your V, right? So then what I could do is I could look at this chi-V tensor, you know, blank equal to 0. So, you know, use this as a variable. So like, you know, we wanted to find, I have my moduli space V1. We need to find V2 such that this Euler characteristic is 0, right? So what you can do is, maybe let me call this V1. And then let me leave the V2 as a variable. So this V2 is a variable. So then if you look at that, then you get the quadratic polynomial again by Riemann-Roch, right? That looks like this. So, some quadratic polynomial, okay? And then what we want to say is the following. So you see, this quadratic polynomial will intersect this Drezil-de-Poitier curve along a peak. That's not entirely obvious, right? You might worry. So you know, the way you should think about it is that around each exceptional divisor, there is a nice region where these peaks define for you, like, what are the obstructions to the existence of stable bundles. If you remove all these peaks, then what you get is the Cantor set on the line delta equals a half. Okay? Like, a priori, you might worry that this Euler characteristic thing that you wrote down passes through one of those Cantor set points. I mean, how do you know that this thing doesn't come here and then, you know, pass through a Cantor set point, right? And that's a sticky thing that you need to do. But the key point there is that, you know, if you do that, I mean, you know, you need to prove a theorem that says that those points are actually all transcendental numbers. You know, I said before that they were not rational numbers, but in fact, they are worse than that. They're all transcendental. Because this is the quadratic polynomial, you never pass to something like this. You really intersect the curve in some nice way, okay? This is a technical point that you do need to resolve, but, you know, I'm not going to worry about that. And then, you know, you can ask, so then, you know, the kind of thing that you should think about is that there is, so to speak, like a lower slope stable bundle that this parabola intersects, right? I mean, you know, it's basically if it's meeting the curve in some point. And the way you should think about it, at least when you're talking about the Hilbert scheme, is the Brill-Noether divisor defined with respect to that stable bundle as the one that you're looking for. Okay? So let me write that down. Maybe let me write down the theorem correctly. Okay, let's actually state the correct theorem rather than the vague theorem. So like here is the situation. You have some exceptional bundle E alpha here, and you have the peak of the Dressel-Lepotier curve, right? And you know, there are three possibilities with what your thing can do. It can pass through here, I guess. It can pass through here. It can pass through here, or it can pass through here. And now what's the difference between these? The difference between these is that you see whether this parabola passes above, or it passes through E alpha, below E alpha, or it passes above E alpha. Okay, so those are the differences. And how do you tell the differences? The sign of chi V tensor the E alpha, the chunk class, chunk character of E alpha. Whether this thing is equal to 0, greater than 0, or less than 0. Greater than 0 or less than 0. Okay, so there are three possibilities, right? And then if it's greater than 0, actually there are two possibilities. It could pass, it could intersect the right-hand side of the curve or the left-hand side of the curve, okay? The only slightly tricky case is that when you intersect this, when you're like this, then you need to sort of take this point of intersection, okay? In all other cases, you take this point of intersection, okay? Let me call this thing mu, let me call this thing mu, let me call this thing mu, and let me call this thing mu, okay? So then the theorem is like this. So the effective cone, the extremal ray of the effective cone, in fact, not just of the Hilbert scheme, but really any moduli space, I guess we were calling it V1. V1 is the Brill-Noether divisor associated to a general bundle of sufficiently large rank of sufficiently large rank. In, you know, the moduli space mu in let me multiply it. So in other words, you see there is a moduli space of stable sheaves at these points mu, right? So, but you see these are up to scaling, so I can scale like, you know, it's really, we remember we are drawing this thing in the mu delta plane, right? Like this doesn't quite determine the Chern character. I have the rank, right? If I find some integer character there and multiply this integer character by larger and larger numbers, I get like different moduli spaces. So you take something of sufficiently large rank to moduli spaces corresponding at these points. So then you take the general Brill-Noether divisor, and that's the extremal ray. Okay. So far, all the examples, of course, I've talked about, actually, this was passing through this exceptional thing. It was OF1, OF2, the tangent bundle. We've only talked about, you know, these exceptional cases, but in general, the answer corresponds to the way, I mean, informally, the way you should think about it is that, you know, you take the minimal slope stable bundle such that this Euler characteristic is 0, subject to the condition that the slope of this product is non-negative. And you take a sufficiently large multiple of sufficiently large rank 1 with those invariants, and the Brill-Noether divisor associated to this will give you the extreme array of the effective cone. And that's a slight lie, because in this case, it's not this point that you take, but it's that point. So you sort of, if your Euler characteristic is positive, then you need to take the one that comes from the left edge of the Drezl-Potier curve. Okay? And again, let me explain, how do you prove this? How do you prove? I mean, I'm not going to give you a proof because we don't have time. How do you prove something like this? The key point here is that, if you want to compute cohomology, you need a resolution. And, the resolution that you take is determined by this exceptional bundle. So, the exceptional bundle E alpha determines a resolution. So there are two things that happen. So first of all, the moduli space, the general member of the moduli space, let me write it as M mu if you don't mind. I should say really R mu, but in this moduli space, M mu has a nice resolution. And then the general member of M P2V, you get a resolution to this E alpha. And the point is that now once you take this nice resolution, the vanishing of cohomology becomes obvious. Then the vanishing of cohomology becomes obvious. So the picture that you should have in mind, when we had the tangent bundle of P2, then the resolution that I wanted to take for IZ was this one, for the general point of this, right? But in general, what you're going to do is there will be an exceptional collection associated with this E alpha, right? That you're going to use in order to resolve simultaneously both your general sheaf in M mu and your general sheaf in this moduli space that you're interested in. And what happens is that then you can tell that the cohomology vanishes. All right. I'm going to stop here because unfortunately I ran out of time. Otherwise, I would have told you more about it. But tomorrow, what I'm planning to do is introduce Bridgel instability and explain how you can use Bridgel instability to find these kinds of resolutions. Like, you see, the issue here is we started by saying that if I have any vector bundle, right, then I can filter this into semi-stable vector bundle, right? But if you have a stable bundle, right, then there isn't an obvious way of filtering it anymore, right? It's semi-stable. I mean, what are you going to filter it by? So now what we are going to do is by shifting our category, we'll find a way of destabilizing this and then finding canonical resolutions of this bundle. And for that, we are going to need Bridgel instability. And so what I'm going to do next time is briefly introduce Bridgel instability and do some examples of how you find resolutions and compute cohomology. Let me stop there and see whether there are any questions.
No more questions. So thank you very much.
I have a question. I have a question.
Okay,
oh,
yeah.
Okay.
If you go back to the fractal picture.
Yeah.
Go back to that.
Yeah.
The earlier one.
The earlier one. Okay. This one?
Yeah.
Okay.
No, maybe the one before that. The
one before that. I drew this thing over and over again. Okay.
Yeah. So you said the discriminant should be less than a half. What is that for?
Oh, so this was if you were exceptional. if you are exceptional, like, so the way you should think about this is that there is a half, right? So, like, you know, the way you should think about it is that, first of all, there are no semi-stable bundles of a discriminant a half on P2. Like, on some other surfaces, like on P1 cross P1, for instance, there are such bundles.
Yeah.
And that makes the classification much harder. But on P2, you don't have any semi-stable bundle with discriminant a half. You can have, if you have a semi-stable bundle of discriminant less than a half, then it has to be exceptional or semi-exceptional. So it's one of these things that you get through mutation or taking direct sums of. Like, you know, I could always have O of 3, or 3 copies of O, for instance, and that would be semi-exceptional. Okay.
So you said if the discriminant is less than a half, then it's exceptional?
It's exceptional, and all the exceptional ones were discriminant less than a half.
So, for example, the O is just at the origin.
Yeah.
So what is the peak above O?
What is the peak above O? Sure. So, like, the way you should think about this is that it's like IP, for instance, sits at that peak. But in general, the way it looks like is like this. So I don't have space, but maybe I should stay here. And maybe let me just, let's write in a different color so that maybe we can. Okay. So in general, a member of that moduli space looks like this. So you have O of minus 1. You have, I think it looks like this. So you have O of minus 1, 2a, O of minus 2a, and then it's a co-curve of that.
Yeah.
In fact, I think every member of that moduli space occurs this way.
Okay.
This is not
so
obvious.
above each exceptional, there is a peak. Is that correct?
Right. So I mean, you know the moduli spaces that lie in here, in these guys, really well. They are moduli, they're Kronecker moduli spaces.
Yeah.
So I mean, what I should have said is that, so like they are spaces of Kronecker modules. So what they are is that it's something like this. So you have two exceptionals. So the way you should think about this is that these are orthogonal to this exceptional, right? So these fit, like each of these exceptionals fit in strong exceptional collection, and corresponding to each side of this thing, you have two exceptionals. So the two exceptionals here are O of minus 2, O of minus 1. Here, I believe they are O of 1 and O of 2, right? So let's do it for these. But if you chose any exceptional, you could tell which two exceptionals are the orthogonal ones that define that. And so what it is that along this blue ray here is that you have a Kronecker module going from O of minus 2 to O of minus 1. So there are 3 arrows there, right? And then you put a vector space dimension A here and a vector space dimension B. Okay? And then you look at all, you look at all possible such objects modulo the action of GLA here and GLB here, right? Then there's a GIT quotient to that thing, and that's called moduli space of the space of Kronecker modules. And along these arcs, the moduli space is actually isomorphic to the Kronecker moduli space. That's the theorem of Dresden. So in particular, in that peak, there are 2 ways of viewing the moduli space. But if you want to know just the simplest member of that thing is IP, the rank 1 case. But as I said, there are ranks, like you can multiply the rank, and typically you'll get something like this, where it will be O of minus 2 to the A going to O of minus 1 to the 2A.
All right. So along the blue curve, you're varying A and B, are you?
Yes, you're varying these coefficients. And then, where the curve ends, of course, has to do when can you not have stable things anymore?
Yeah.
it turns out that life works beautifully in the case of P2, and they all end like when this curve hits a half, discriminant equals a half. And these things really come together nicely.
Okay. Okay, thanks.
Yeah.
Okay, great. Thank you very much for the nice lecture. All right, so
Thank you.
we
So
continue
tomorrow at
Thank you very
30
much.
my time. Yeah. Okay.
Same time tomorrow.
Yeah.
Oh, when will this
Same time.
lecture be uploaded? You put it on YouTube, right?
Yes, sometime tomorrow, today.
Okay. Yeah. Maybe I want to rewatch some parts.
Yeah, we do sometimes. Yeah, great. Yeah, I'm gonna do it as soon as possible.
Yeah. How are you doing, Mustafa?
Yeah, hi.
How are you doing? Where are you?
All right, better.
Yeah.
Are you back?